Hello guys, welcome back. We're going to begin lesson number 3 now. Lesson number 3 is going to be broken down into 3 videos as well as lessons 1 and 2 have been. The first video we're going to talk about is the definition of the derivative. The definition of the derivative, there are 2 ways of approaching that. The second video we're going to do is differentiability. And then the third video is going to be the average rate of change, the instantaneous rate of change, and then a lot of just kind of various questions that relate these 3 videos together. Just a little bit of a review. So I'll do a couple questions on that. So let's talk about the definition of the derivative. In AB, we talk about the average rate of change and the instantaneous rate of change prior to the definition of the derivative, but I think that it's okay in BC for students to kind of understand this concept. But if this doesn't quite make sense to you, I would encourage you to go look at video number 3 first of this lesson and then come back and see what we're doing here. But you don't really need to know the average rate of change and this instantaneous rate of change, how to find those to understand this approach. So what we're going to do here is we're giving ourselves a function, right? This function right here, this parabola, and we are looking for a line. So we've created ourselves a line, and this is a secant line. You guys remember from geometry, I know some of you guys, you hear that word and you hate it, geometry, but you were introduced to what we call a secant line, right? And the secant line is a line that goes through the circle at 2 different points. And so this is exactly what a secant line is. It's connecting 2 points on this parabola, and we created a line with it. We're going to go ahead and call this value, and let's just pretend right now that this is on an XY axis. Okay, so let's just go ahead and make this Y and this X. And so the point here at P, we're going to call this our X, and then we're going to call this point down here X naught. It's just changing. It's just, this could also be A and B if you want to. It's just our first X, and this is our second X. The distance between these 2 values, these are our delta X. Right? This is what delta X is. So how much is it changing? So for example, if this is 3 and this is 7, then delta X would be 4. Right? So we're just choosing some X value here and then another delta X or another X here. All right. So with that being said, then the equation of the secant line would be f of x naught. Because if this is x sum naught, then over here, this would be f of x sum naught, right? So if this had been 3, this would be f of 3. So that's where you get with this. This is x, so this area right here just would be what f of x is. So that's where this equation comes from. Now it looks pretty complicated, so I'm going to, in my box here, I'm going to show you guys a much easier, nicer way of doing it. But I want you guys to just see what the notation for this is, and that's where they come up with this equation. So what we want to now do, and I'm going to go ahead and erase this whole part right here for you, because I want to talk more about, now let's talk about the derivative of what we're doing here. So I want to eventually make my values. So again, I'm going to go ahead and draw my little axes here. So let's keep that. And this is still my x, and this is still my x sum naught. And so what I eventually want to do is I want to be able to get these points to get really close to each other, right? So I really want them to get really close to one another. So you guys can see that. Well, how can I do that? Well, I can actually do limits. I can make them start approaching each other just like we've approached asymptotes in previous videos. So I want to go ahead and create a function, right? So I'm going to go ahead and create, here's my parabola again. And I want them to get really, really, really close together to where they actually end up being at one singleton point. And then we're going to go ahead and create a line that goes to that point. And now we've created ourselves a tangent line. And so what's really happening here is if we were able to take the equation of our secant line and we were to implement the limit as this x approaches x sum naught. And really what this is just that this is getting closer together. They're getting closer. X is approaching x sum naught. So it's going, now P is here. And now we got the secant line that looks like this. And now P is here. We got a secant line like this. And then P eventually gets to here. And then we get to this lovely drawing that you see right here. So what does this mean? This may be confusing to you guys, but let me just go ahead and now say, what does this all mean? We really want the equation of the tangent line. And if you guys look at example number 1 here in the bottom, it says find the slope of the tangent line. Well, that's where, ladies and gentlemen, that's where our 2 points have kind of gotten together, where our delta x, our delta x is actually now become 0. Okay, delta x is now 0 because the points are now on top of each other. So if this doesn't make sense, here's what you got to do. We're given the find, in example 1, it says find the slope of the tangent line to our function. We don't need to graph it, and it's telling us a value. We want to know at a particular value. So if you're given a value, then you're going to use the formula that I'm going to say right here. And it's so awesome and so basic to do. So we're going to take our limit, and we're going to take x, and we're going to approach that value, right? So we want x to get closer and closer and closer to 1, to where now this horrible picture that I have right here, this point, actually hold on for 1 second. Okay, so off camera, I just drew, again, not so great picture, but just to give you guys an idea of what's going on here. So I've got my polynomial, and I've now made P and Q to the point of this value here, and I'm trying to find where this point approaches A, right? So this is my random A. So again, we have the slope of a tangent line, so it does end up being a tangent line because it's just touching this curve at that one particular point, right? And so we're approaching 1. So if you're looking at this limit as x approaches A, then we're going to take the function and we're going to subtract f of A all over x minus A. So this is the equation that we're going to use. This is the equation we're going to use for this. And so we're going to do the limit as x approaches 1. And so the first part of their equation is just what f of x is. It's given to us right here. It's going to be 3 minus 2x minus 2x squared minus, I put parentheses around this, I want to plug in now what f of a is. Well, a is 1, so what is f of 1? So we're going to evaluate this function with a 1 plugged in. So I'm going to plug in 1 here, and I'm going to get 3 minus 2 is 1, minus 2 is negative 1. And this is going to be all over x minus 1. So I've now taken the equation, x is approaching this value of a. We want to come closer to a, right, of our function. And again, this is our slope of our secant line, but this makes it our slope of our tangent line. So then down here, we're going to find the limit as x approaches 1. And this is going to be negative 2x squared minus 2x plus 4. All over x minus 1. And then I'm going to do one more quick thing. And notice, again, ladies and gentlemen, and I've stressed this in previous videos, I am constantly bringing limit, right? I'm doing the limit. I'm taking a negative 2 out. I've got x squared plus x minus 2 all over x minus 1. And now the rest of this, we just kind of go with what we have learned in the previous lessons. We would plug in 1 to the top. We would get 0 on the top. We plug in 1 on the bottom. We also get 0 on the bottom, so we have to use a little bit of algebra skills for this. And like I said before, if you're going to do this, most likely when you factor, one of your terms will be x minus 1. There's no surprise here that it is x minus 1, and the rest of them is going to be x plus 2, right? And that's going to give you your function for this. And then we're going to cancel out our x minus 1s. And I'm running out of room here, so I'm going to put this little guy right here. So we're going to have the limit as x approaches 1 of negative 2 times x plus 2. And we're going to now do substitution for this, and we're going to get negative 6. Right, negative 6. So hopefully that makes sense to you. So what that means is that the function, if I'm looking at the function, and I take its derivative. And I'm going to tell you guys right now that students, they get this, they're like, oh my god, this is a lot of work. When I show you guys lesson 4 and I show you the power rule, this question is really, really easy to do. But I have seen there are times where they ask you to use the definition of the derivative to solve these problems. And so this is what you would do. All right, so let's move on to example number 2 and see what we can do with this one. So for this example, it's asking us to find the slope of the tangent line. It's given us the function and it's telling us that this is at x equals 2, which again just basically is a equals 2. I'm going to assume here that I'm going to tell you that we want to use the definition of the derivative. If this is not the case for this, so again, lesson number 4, we would actually apply derivatives to this. But right now, let's just go ahead and use the definition of the derivative so you guys can see it one more time. So if you were a little bit confused about example number 1, then maybe this will help you out with what we're doing. So again, limit as x approaches 2. The first thing is our f of x. So we literally just write our f of x here. Then we're going to subtract what f of 2 is. So off to the side here, we're going to plug in 2 to this, and we're going to get 1 over 2 minus 1 is 1. So f of 2 is equal to 1. And this is going to be all over our x minus 2, right? So I basically just did this little formula right here. All right, so that's what I did with that. It's pretty straightforward. Again, if you plug in 2 to the top, you get 0. You plug 2 into the bottom, you get 0. I want you guys to understand that we've done problems like this before, right? This is where in the algebraic part of this lesson 1, I want to say, we talked about how to do this by combining fractions. So I'm going to go ahead and do that. I'm going to get 1 minus parentheses 1 minus x minus 1 over x minus 1 all over x minus 2. If you did not understand how I was able to get from this step to this step, I did talk about that in my lesson 1 videos. I think, again, it was part number 2. So we're going to just combine fractions is really what I did here. And so I've got a fraction over a fraction. I'm going to go ahead and simplify this a little bit too. And if you guys can look at this, it's going to be, make sure we keep our notation, right? Keep our notation. So limit as x approaches 2. I was just getting very excited about simplifying this that I completely forgot about the limit. Never ever lose your notation, especially if you are doing you're dealing with variables still. So it's going to be negative x plus 2 over x minus 1. And then we're going to still big line here for this, and then it's going to be x minus 2. And so hopefully this is going to start making sense to you guys now of what we're doing. We're going to do the limit again. X approaches 2. I'm going to go ahead and pull out a negative in the top here. So it's going to be negative, and it's going to be x minus 2 all over x minus 1. If you're dividing by a fraction, you multiply by its reciprocal. So I'm going to go ahead and do this. And then this is good for us because now things are starting to cancel out. And when we do this, we're going to get the limit as x approaches 2 of negative 1 over x minus 1. We can now do substitution for this problem. We plug in 2 here. We get negative 1 over 1. So our answer is going to be negative 1. So the slope of the tangent line of this function at x equals 2 is going to be negative 1. So that is the first, and I hate to say it, but the easier one of the 2 approaches that we want to do. But again, ladies and gentlemen, I encourage you always and forever to use this limit definition for the derivative if you're given what a is. It is literally number f of x minus f of a over x minus a. All right, so let's get down here with this one and try it if we don't have a value or we want to try another one. And let's talk about this one now. Okay, so off camera, what I did really quick is I drew another little picture. I want to say again, for the very first example, we were making where the 2 points were approaching each other, right? So the 2 points were approaching each other. Well, what if we change it up a little bit and we drew another graph, kind of very similar? I still call this point x, all right? And again, let's just say that's 1. And then we have a distance of, let's say, 4. So let's say h is 4. So this right here, this point would be x plus h, right? X was this distance right here. This is h, so this would be x plus h. So there's that. So if we want to, we can now say, again, this equation would be the slope, because over here, this would be f of x plus h. And guys, you don't have to get burdened down by all of this stuff. I'm just trying to show you guys where the equations are coming from. But as long as you can understand my, I tell my students, if you understand just the content of how I'm doing the examples, you will be fine for this. But the next approach is, okay, well, let's make, instead of these points coming closer to one another, let's change the distance between the two. And let's make that distance, that change in h, actually approach 0. So when h gets to be 0, then these points actually become 1, and then the tangent line also increases. So you can look at it h. These are the exact same examples. It's just that one is in terms of h, and then the only difference in this versus this other problem is we are, instead of changing it to h, we're going to just do, this is now a delta x, and this will be plus delta x. Either one's fine. It's the same thing, and we want to now use the same concept with this. I like the h one because it's just a little bit easier for us. So we're going to do this one now. And usually you use the definition of this derivative when you don't know the value. Now they're telling us what's happening at x equals 1, 4, and 9. But we're going to say let's use the definition of the derivative to find the slope of the tangent at any point of y equals the square root of x. So we're going to use this to figure out values. But right now let's just say they're not giving us the a. We want to find the equation of the slope of the tangent line of y equals the square root of x for any value. So it's always the limit as h approaches 0. And so the first thing we need is so this right here, f of x is equal to the square root of x. So the first thing we need is f of x plus h. Well, everywhere you see an x, you just make it an x plus h. So pretty straightforward. So we get the limit as h approaches 0. F of x plus h is now the square root of x plus h minus our function, right? That's just our function. Our function is just the square root of x. And then our denominator is just simply h. And again, ladies and gentlemen, if you plug in 0 here, you're going to get the square root of x minus the square root of x, which is 0. You're going to also get 0 down here. So then what we're going to do is we're going to multiply by the conjugate, right? And we've done this in a previous video as well. So this should not be brand new to you as well. Oops, let me actually go ahead here. Okay, so I'm going to go ahead and multiply by the conjugate. I don't know why I'm writing down. It's weird. And so what's going to happen here? So when we do this problem, we're going to get the limit as h approaches 0. The top, these are going to cancel out, and you're going to get x plus h. This term and this term, the o and the I, actually do cancel out, and then you're left with the negative x. So everything that's on the top is just going to be h. I told you guys in the previous video, when you're doing conjugates, there's one that has no radical and one that does. You do not distribute them. You leave them alone. And I'm going to save a little bit of time here and know that this cancels with this, and then the h's cancel with this. And so what we're left with is the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And all I'm doing here, all of this is that we're taking the formula that we have, we're plugging in x plus h everywhere we see it, and we're going to do another example in a minute with these problems, and then we're following our formulas, and we're getting to this right here. And once we plug in 0, we're going to get the function answer. And I know I still got variables in here, but this is the general equation for the slope of any tangent line at y equals the square root of x. And so that's what you would do for this. And then what they want you to do is plug in now f prime. You guys will get to this notation in the next lesson, which is going to be 1 over 2 square roots of 1, which is just 1/2. So the slope of the tangent line of this function at 1 is just going to be 1/2. You do 4, it's going to be 1 over 2 square root of 4, which is just going to be equal to 1 over 4. And then f prime of 9 is going to be 1 over 2 square roots of 9, which is 1/6. I have students that are taking BC that took AB with me last year, and they're like, oh my god, there's such an easier way to do this. Yes, there is. I am aware of it. I know that just taking the simple derivative of this and plugging these values, giving these numbers. But the point that I'm making here is that the definition of the derivative is important, and you have to know how to do it. You have to know how to do it. Okay? So what we're going to do now is we're going to do 2 more problems, just 2 sample questions, just to reiterate what I've done with these problems right here. Okay, so let's. Okay, so we're going to start example number 1. This says use either definition to find f prime of 1, which is our derivative, which is going to be the slope of our tangent line, if our function f of x is equal to 1 over x. And then over here, we're just basically finding f prime of x, right? So we're not given a value. So in this one, we're going to use version 1. So let's just real quickly write up what version 1 was. And that would be this formula right here. So the limit as x approaches a of f of x minus f of a over x minus a. So a clearly is 1. So f of a, or f of 1, is just going to be 1 over 1, which is 1. So we have everything that we need now to actually solve this problem. So we're going to write the limit as x approaches 1, because that's what a is. A is 1. And then our function is 1 over x minus 1 over a, which is 1, all over x minus 1. And that's basically it for the setup. And then just like we've done previously, and I'm going to go through this very fast now, we get our common denominator. And there actually may be a time where I think we actually did something very similar to this in one of our examples in the previous videos. So we went ahead and got our common denominator, and then we're going to pull out a negative in the top. And the reason I know to do that is because I need to cancel stuff out, and I see this is 1 minus x and this is x minus 1. So I know initially I'm going to cancel that out. And so now I'm left with this. And luckily for us, we are able to cancel. And then we're left with the limit as x approaches 1 of negative. Please do not forget about your sign. Negative 1 over x. And if we plug in 1, we're going to get negative 1 again. Okay? So the slope of the tangent line at x equals 1 is actually equal to negative 1. So that's the general easy way to do it. And I'm telling you, you want to use this limit definition when your value is given to you. All right. Now again, lesson number 4, I'm going to say this many, many times. When I show you how to find the derivative of this problem is ridiculously easy. But it's really good for this for notation and for your algebra skills. Now, I'm not going to finish B. I never finish it in the class because it becomes so gross. But I just want to set it up for you. My answer key for my students that are watching this, my answer key, I did finish it, so you can see this craziness for what's going on. The first thing I just want to say about this problem is that we want to find the derivative of this, and I want to just say as a good algebra technique, and we'll talk about this throughout the course, we can split this up. So I don't like how this is written, so I'm going to say instead of writing like this, I can do x over this, I can do x over this, I can do x over this. I can split my numerator, right? Because if all my fractions have the same denominator, then I can really just do this minus this all over 1. So I just want to preface by saying that I'm going to rewrite my function a little bit differently before I even start the problem. And then I'll write up what the limit is for our notation, and we'll be good to go. So this function is really just 2x minus 3 plus 1 over x. Right? That's really what this essentially is. So it's really nice to simplify this out as much as we possibly can before we start the problem. So we're going to use the definition of the derivative of this one. So it's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? So I'm just going to set this one up because, like I said, it does get pretty gross. So the only thing that we actually need here is what f of x plus h is. That's really all we need. Because we know what the function is. It's given to us right here. And then h is just still h, right? And this is 0. This will always be 0 in this problem. So everywhere you see an x, you are literally going to write x plus h. And that is as simple as that. So I've substituted in x plus h for everywhere I put in an x. So let's do this. And you guys will see how absolutely gross this is. But it's just nice to do it. Like I said, on my answer key, I've done that for us. So this term right here is what you see right here. And I'm going to go ahead and start distributing while I do this. And now, one thing I have not stressed yet, and I'm going to change colors to kind of stress this with you, so that it's minus, and then this is f of x. If you do this correctly, if you do this part correctly, then everything that's in here will cancel out. Everything in here will cancel out. Now this example, you can see that the 2x is going to cancel out with the 2x. The negative 3, and this is positive 3, is going to cancel out with this. So you have a 2h, and you have this 1 over x plus h, and you have a 1 over x right here. When you start simplifying things down a little bit more, then this will also cancel out. Okay, you cannot split this up. This is not 1 over x plus 1 over h. I know you guys are calculus students and you know that. that that's not it. Actually, let's do this. So if anyone's watching this video that's not one of my students, and you're like, let me see how this is done, let me actually show you the answer key so you guys can look at it. We can talk about it a little bit more. Okay, so I went ahead and just shared my answer key with you guys. We were at this value right here. This is where we stopped. What is so gross about this particular problem is that you have now 3 fractions that you have to get a common denominator for. And so that's what I did right here. And that's why this whole thing right this. And then I was able to then just, so this whole section right here, this little box, is this top part. And then since I'm really dividing by h, I'm really multiplying by 1 over h. You simplify here, you simplify, I got my screen blue, you simplify here, and you keep simplifying till you get to the point that it's 2x squared minus 1 over x squared. I will say that I don't personally expect my students to do this much work because 1, there's a lot of possible algebraic mistakes. 2, it takes too much time. And 3, there's a much easier way to do the problem. So I'm thinking that I'm just showing this to you guys just to see that sometimes math can get a little bit crazy, but it does work out in the end. So definition of the derivative, we're going to come back in video number 2 and talk about differentiability. And then, like I said, we'll go back to average rate of change and instantaneous rate of change, and then do some mixtures of questions in video number 3. So I hope that's helpful, and I will see you guys in the next video.